Hi friends! Do you frequently rely on Google Maps to calculate the shortest distance from your own location to another place? And you were curious how you can make similar computations and maps in R? Well, look no further because in today's tutorial, I will show you how you can do exactly that. We'll be using the dodgr package in R, which will leverage the OpenStreetMap data and then do some computations and create some awesome maps that will show you the shortest route from your specific location to any other points of interest. We'll kick off our adventure by installing and then loading the necessary packages. Here I'm gonna start off by creating a list of package names that we need, and the first one is the tidyverse umbrella package, from which we'll be using dplyr for data wrangling and ggplot2 for data visualization. The second one is the OSM data package, which we'll use in one of the previous tutorials, from which you can get basically any point of interest or roads from the OSM data, and we will use this one to get the fuel stations and also roads for Belgrade. The third package is the dodgr package, which we haven't used before, and this one we will use to compute the shortest routes and shortest distances from our place to the point of interest. We'll be using a lot shapefile, so we definitely need to load the SF package. I would also like to use the street layer view for Belgrade, so that's why I'm using map tiles here. And finally, to plot these street layer views, I will definitely need tidyterra. Now that we have the list of packages that we want to install, we first of all need to check if they are already installed. So I'm going to create an object here, and then I'm going to use this libs list, and then I'm going to go into the row names of already installed packages. So then if it's not installed, I need to install. So here I'm going to write an if-else statement. So if any of these installed libs equals false, in other words, if it's not installed, then we need to install them. So basically we need to say install .packages, and then we need to get from this list libs, we are installing those that are not among the installed libs. All right. And then the final thing here is that some of these packages are going to require also dependencies, so we also need to put here dependencies true. Okay, so this is going to install the packages that we need, and the final step is to simply load them into our session. So that's quite easy. We just need to apply the library function to this list libs, and the library function in R is used for loading packages. Okay, so in this tutorial, we'll be working with the extent of Belgrade. So here I have coordinate points for the rectangle over certain area, which I got from the FindBbox website. And if you're not sure how to also fetch for your area interest, you can check one of my previous tutorials where I explain in detail how to do that. So over here, what I did, I went to FindBbox, I got these parameters for that rectangle, and then now I need to sort it out and then use them for cropping the street layer and other things that we need. So this first value is the minimum longitude values. So I'm just going to name it here xmin and pass it here. So notice how I'm using all these decimals. You should also do that, because I figure out that if you don't do that, there might be a problem later on with dodgr. So as many decimals as you can, that's the advice. The next one is the minimum latitude value, or ymin, so we can just paste it here. The next one is the maximum longitude value, or xmax, so I'm just going to also pass it here. And then the final one is the maximum latitude value, or ymax, also pasting it. So now that we have this, we are ready to actually create a bounding box of Belgrade, which we will actually after that use to pass it to the OSM data. That's why we're using, because OSM data accepts certain extents. Okay, I'm going to call this one Belgrade bbox, and then I'm going to go ahead and create here a list. All right, so a list will have the following members. It's going to have this xmin, which is going to be equal to xmin. It's going to have then ymin, so it needs to be in this order so that OSM data can work with it. Then we have xmax, which equals this xmax that we already defined. And finally, ymax equals ymax. Okay, so this is where the SF package kicks in, because we want these, just like numbers, we want to create a polygon out of them. Or actually, we want to create, first of all, a bounding box and then a polygon, which is going to be basically a rectangle. So how do we do that? Well, first of all, we need to define what is the coordinates reference system that we're using here. It's the just WGS84, so we can easily do that. So the first thing is, as I said, create a bounding box as an SF object. So here we define it, the coordinate reference system, and then we can turn this bounding box then into a rectangle. So for that, we can use, again, SF package, and there is a function from it, which is called STSFC. So here we simply need to pass once more, confirm that the coordinates reference system for this rectangle is going to be WGS84. So the first use case for this bounding box is to use it to get the street layer view for this extent of Belgrade. And this is where map tiles kicks in. So I'm going to create an object called Belgrade streets. And then I'm going to call to rescue map tiles, and especially its function, which is called get tiles. So this is going to give us a CartoDB positron view, but you can actually check different providers. So here we're going to pass this Belgrade VBox that we created, and then we're going to pass the provider that we want. So this provider has several options, and actually if I show you quickly just here, you will see that it's a bunch of them. So you can even use OpenStreetMaps if you want. I'm using this specific one, which is CartoDB positron, because it has basically, it's kind of a gray, on a gray scale. So that will allow us to have colored lines and points. So I'm just going to go ahead and call it CartoDB and then dots positron. All right, and then the last one is the zoom level. So here, the higher the zoom, the more it is going to be zoomed into your location. So I found that 16 is an okay zoom. It's going to take a bit more seconds to kind of load this, but the end result is kind of it does actually zoom it in quite a lot. So I'm happy with the outcome. Okay, now that you run this, we can actually check if we got really what we needed for that extent. So here I'm just going to build a query using ggplot2, and here we're going to actually use tidyterra, as we said, to plot these spatial rasters that we have. So here we just need to pass that the data equals 2 and then Belgrade streets, and then once you run this, you should be able to see the street view layer of a part of Belgrade. So in this tutorial, we'll be calculating and then mapping the shortest distance from a certain point to a fuel station. And to get the fuel stations for Belgrade, the easiest way would be to get data from OpenStreetMap. And for that purpose, we'll be using the OSM data package. So here I'm going to create an object called Belgrade amenities. And here I will be calling, as I said, OSM data. And it has a very useful function, which is called OPQ, which can fetch the data for you based on the bounding box. And speaking of bounding box, here we need to pass it. And luckily for us, we have this Belgrade VBox that we created. Now, there are two optional arguments that I include, because sometimes the data just cannot be in time, and then there is like a timeout. So I actually extend this timeout here. I put it to 180 seconds. And then also I increase the memory size here to some, I don't know, random number, a very high number, so that you don't end up in a situation where, you know, this returns an error and not the object that you want. Okay, and now that we defined for what we need and these optional things, now we can get to the features. So again, we call OSM data here, and then here add OSM feature. So that's the one. Now here, if you're not familiar with the OSM, the whole dictionary of items, maybe you can check the link, which I will provide in the description box below. The one thing that for any point of interest here, such as shop or fuel station or supermarket or, you know, any kind of other, I would say, commercial object, you need to use here a key, which is amenity. Okay, and then for value here, because we want a fuel or a fuel station, then we need to choose fuel. If you're interested in maybe some other amenities, again, you can check the link. Okay, so, and the final thing here is to get these into an SF format. And luckily for us, OSM data has also that great function, which is called OSM data SF. So it's going to basically coerce this into an SF object. Okay, so once you get this, you will actually have points and polygons and lines. We obviously want points. So I'm just going to put here a new thing, which is Belgrade fuel and then PTS for points. And then I'm gonna get Belgrade amenities here. And then from Belgrade amenities, I'm going to take only object which is OSM points. So other objects are OSM polygons and OSM line strings. So this is what we need. Okay, and once we do that, the only thing we need to do is, because this comes as a list, we basically just need to put it together, so unlist it. So this is how are we going to do that. I'm going to call this Belgrade fuel. And then I'm going to use do call here. And then within do call, I'm of course going to use rbind to bind these row-wise once I unlist them. And I'm going to actually do that with this object. And then finally, I don't need all the things from this one. It has a lot of things OSM data usually has. So I'm going to only select two that I need. One is OSM ID, which is going to identify each of these in case we need that. And the second one is, of course, the geometry field. And now we can also visualize this. So we're just going to go back and take actually this previous chunk. And then within this chunk, what we're going to do is we're just going to add one more line, which is accommodating these, of course, petrol stations. So I'm going to here go and write GMSF because this is an SF object. And then for data, I'm going to pass, of course, this Belgrade fuel that we just created. And then for the color, perhaps we can just go for black. That's totally fine. It needs to go actually under quotation marks. And then importantly here, we don't want to inherit the aesthetics here. So inherit AES equals false so that we don't end up in a situation where we cannot actually see these points. Actually, let's make them blue just for fun. Okay, so and then when you run this, you should be able to see the street layer view, but also the blue dots indicating the fuel stations for this extent of Belgrade. And then our next step is to get the OpenStreetMap roads, which we'll be using for calculating, of course, the shortest routes along those lines from our point of interest to any of these fuel stations. So I'm here going to create Belgrade roads object, and then I'm just going to paste the previous one, which actually used for getting those fuel stations, but we will change something. So this first part will stay because, again, we need for this bounding box of Belgrade, we need to get the data. But here for this key and value, we actually need to change key to highway. In the glossary of OpenStreetMap, highway are basically all the possible roads. And here for value, we're not going to take any specific value. So we're going to take all the possible roads. So we allow dodgr to use any kind of a road to build actually a model for us of getting to the shortest route by motor car. Okay, and then this is also gonna stay. And then the final one is simply to from this Belgrade roads, take only lines. So we can just go ahead here and just write get OSM lines. And then the new object can be called, for example, Belgrade highways. We can go ahead now and add roads to our codes that we previously used to plot fuel stations. So here I'm just gonna go ahead and add GMSF once more. But here now for data, I'm gonna add these Belgrade H-ways. Here I'm gonna go for color, which is black. No worries, there are gonna be a lot of roads, but I'm gonna control this by actually putting a bit lower size. So I'm gonna go for 0.15. And also the transparency level, I'm gonna set to 0.5 out of 1. And then finally, I'm also gonna add this one that I don't wanna inherit the main aesthetics. And the last one is to actually get rid of that excess of those grids using theme void. And then actually once you run this full chunk, you should be able to see now the street view layer, but with added roads and also the fuel stations. In order to do our analysis to calculate the shortest route, we first of all need to decompose roads into distinct edges and to create a network that we can then use for calculating these distances. So I'm going to go ahead here, create object G, which is going to be this network graph. And then I'm going to call dodgr and its function, which is called weight a street net. So basically this one is going to calculate these networks, it's going to compute them, and then it's going to assign weights to each of these distances based on the mode of transport that you chose. So the first thing that we need to put here is the object which contains roads, in our case Belgrade HOAs. The second one is the weight profile. Basically, this one is exactly what is gonna be used for weighting. There are several ones, of course. There is foods, there is a motorbike, there is a motor car, and we're going to be using here a motor car. So what is the shortest distance from a certain point to any of the fuel stations if you travel by car? All right, so you can actually check here what actually also is there. There's also a horse, wheelchair, bicycle, moped, different kind of things. So very, very, very interesting one. Okay, and then the next one is what is the type of column from this OSM data that we need, and we need the one which is highway, because remember in the glossary of OpenStreetMaps, highway denotes all the roads. And then if you inspect the first few rows of this newly created G object, you will see what I was telling you about. So we literally decompose the roads into edges, and the column number 2 is the edge unique identifier. And then we also have here coordinates from the vertex of each of these, 2 coordinates for each of course of those vertices of the edges, and then we also have even the identifier for both of these vertices. These are important because they can later on help us actually trace back and find the exact routes, and then also map them that show a way or a route from a point of interest to, for example, the fuel station. So our next task is to compute those different paths and see what is, of course, the distance to them. And for that, we first of all need to extract all those vertices from that graph object, and then choose actually one random that is going to be our starting point from which we're going to be measuring the shortest route to any of these fuel stations. So let's do that by creating an object called V, which is going to be a shorthand for vertices. So V, and then from dodgr, we can use the function which is called dodgr vertices. Okay, so here we simply need to pass this object G that we created. So this is going to give us all the vertices. Basically, it's going to give us those coordinates and the identifier. And then from all these vertices, as I said again, we can take just some kind of a random points along those lines, which is going to help us then compute things. And I'm going to call this one, for example, XY. It can be also points, it can be chords or whatever. So I'm going to take this V, and then I'm going to sample the number of rows of these vertices, okay? And then I'm going to take only one. So size equals 1. So now we have the starting point. So this is basically from. So this XY is from. And we also need 2. So for us, 2 are going to be the coordinates of all these fuel stations that we have. So we simply need to use ST coordinates from the SF package, and then we need to pass here that object which is called Belgrade fuel. And now we're ready actually to write the query, which is going to get us all the shortest pathways from this XY or from to any of those fuel stations. So I'm going to call these paths, and here to calculate paths you need to get from dodgr a function which is called dodgr paths. Here you need to provide 3 arguments. The first one is that graph, so that network of decomposed roads with all those vertices that we'll be using, so that's G. The second argument is from, so as we said, this is this XY object that we created, and the last one is 2. 2 actually equals 2 here. Okay, so we got the list of paths, but we cannot visualize them because they're not in the asset format. So our next task is to match those paths and then convert them into line strings. And for that purpose, we'll be using a nested list apply function. We will have actually 2 list applies. We're going to have an outer one list apply, which is going to iterate over members of the list, where list represents a list of paths for a specific pair of vertices. So from to pair in that street network. And then we're going to have also an inner list apply, which is going to iterate also over members of the list, where each member is going to be a single path, which is a vector of vertex IDs that form the path from to. Okay, sounds a bit complicated, but maybe as we start, you will get the hang of it. So I'm going to create here object called paths SF. And then here, I'm going to go and first of all, write this outer list apply. So this one needs to be the function of this object that we created. So paths, right? Paths. And then this is going to be the function of, for example, X. And then I'm going to open curly brackets. So within this one, I'm going to go for the inner list apply. And here we pass this X here, which is the function that we just created. So we're going to pass that one, and then we're going to create another function, which I'm going to call here y, and then we're going to open the curly brackets once more. So here is where we do the matching, and we put these matches into object which we can call, for example, path xy. All right. So path xy, and then here we need to take this object v because this is where the vertices and the coordinates are stored. And then we need to match. And then we open here the brackets. And what do we actually match? Well, we need to match this one y, so the element y, and we need to match with the column ID, which is from this v or vertex object. Okay. Now, once we are done with this, our next task is to actually transform or coerce this into a line string. And that's quite easy because we can use st line string from the SF package. So here we first need to coerce everything into a matrix so that we don't lose some of the information that exists in that list. And then we can take this newly created path xy. And of course, for line strings, you need to have coordinates of these vertices. So you need x and y column. So here in these brackets, you put first comma because you are grabbing, of course, the columns, and then within this list C, you specify x and y. So once again, this x and y do not symbolize these elements of the function. They symbolize the names of the coordinates in this object. Okay, and then the very last thing here is, of course, to coerce this into a polygon and assign it a coordinates reference system. So once more, we're going to be using st as sfc from the SF package, and then for the CRS or coordinates reference system, we'll be using 4326 to the node WGS84. The resulting object is the list of lists of line strings, but we want to have is a single SF line string object with all those possible routes. So this means that we will need to do aggregation actually twice. So the first one is taking this paths SF objects, and then because it's a list of lists, we need to kind of decompose that into a list. So for that purpose, we're using here list apply or L apply, and then we're applying here again to this path SF. So here we're going to define a function of x where we will simply, basically decompose this. And to decompose this, you simply use here do call. So here we need to do row-wise binding. So the binding of rows. And of course, we need to also have the element list. Okay, so once this is done, we will have now a single list of all these strings. So we need to decompose again this single list into simply an SF object with all the line strings. So again, we're going to take this object here, path SF, and then we're simply going to do here do.call. So we don't need to apply this list apply because we have only a single list. So this will do. And here again, row-wise binding and simply passing also here paths SF. Quick glimpse at this newly created object reveals two important pieces of information. So we have this from to IDs, diodes, and the second information is that we have geometry, which is a line string. So the last very step is to get this into finally an SF format, and then put it back with that street network. Now, for that purpose, we will need to create two columns. We're going to create from and to. So from that paths object, each column is actually to, and the row is from, or actually the starting location. So what we need is we need to multiply each of these from for each of these to. This is how we're going to do that. So we're going to be working off also this paths SF. Then using st as a SF from the SF package, we'll be coercing everything into an SF object. So once again, we're gonna have one element here or one column, which is gonna be from. From is gonna be the repetition. So repetition of names of paths. As I said, those are the two IDs. And then this is gonna be repeated for each row from locations, which is denoted by XY, the previously created one. Then the second one is to. To, again, we need to repeat the names of the paths, which are again two locations. And the times of repeating that is going to be the number of rows of course, XY. Okay? And then once we have this, we can also define the geometry of this newly created object. And geometry is going to be this paths SF object. And it's going to be the first element of this list. And then finally, we need to define the CRS, which is of course going to be WHS84, denoted here by 4326. And now that we inspect this newly created object, finally we can see that it is an SF object. It has the certain bounding box, coordinate surface system, of course the geometry field, and here are those two columns, so from and to. In our case, from is always the same because it's always from the same starting point, but to is going to change because to denotes, of course, to a certain fuel station. And finally, we can visualize, of course, the shortest pathways from our starting point to each of the fuel stations. We'll be working off this previous codes, but this time we're just not going to be using these H-rays. Instead of this, we will actually use two things. One is our starting point, and second one, the shortest routes. So let's actually start off with the starting point. So the data for the starting point is, of course, XY, and XY is not an SF object. So here we need to use actually geom points. And for the aesthetics here, we will need to use X, which equals X, and Y, which equals Y. Okay, we can also choose the color of these points. Let's, for example, use something which is different from blue. Let's say, for example, red. And here for the size, actually we should delete the size, just take the default size. It should be fully visible, so we're not going to take the alpha value. And then the second thing is to add those shortest routes from the starting point to any of these fuel stations. So again, it's an SF object, which we just created. So we can just pass this one, so paths SF, and we can put it here. For the color, we can choose, for example, black once more, but it doesn't need to be, that prominent. So maybe we can decrease the alpha size to, let's say, 0.65 or something like that. And also for the size, it can be a bit smaller. So let's say, for example, 0.25. And we are going to keep also this thin void. So then once you actually run this, you should be able to see only those shortest routes that lead from your starting point to each of these fuel stations. Now you might be wondering, out of all these routes, what is the actual shortest route, which is going to help us decide where we're going to go and buy the fuel for our car. Now in dodgr, it's not so explicit as you might think. We need to take several steps here, but I'm going to guide you through them one by one. So our first step is to calculate the distances here. And I'm going to call this object route distances and then use another function from dodgr, which is called dodgr and then dists or distances. You can take one or the other. Here you need to pass again this graph argument, that's number one. Then you need to pass this from, in our case that's xy. You need to pass to, which is 2. And then the last one is you need to choose here shortest equals true. So this will calculate the shortest distances in terms of meters. But if you want in terms of travel time, then you would put here false. All right, so once we actually have this, we can also check what we got here. Basically, what you will see here is pretty similar to what we had when we were calculating pathways. So what we have here is something like this. So we have a list here where basically every row is that starting destination or distance from our starting point. Every column here is the ID for the two points, so where it's going to. So for that purpose here, we cannot really use this one. What we need to do is turn this into a data frame where we will have one column with distances, another column identifying the ID of that to location. So for that purpose, I'm going to create here a new object, a route distance df, and then I'm going to put this one into a pipe. Remember, this is a list of things. So with lists, we first of all need to convert this one into a matrix in order to preserve that column information that we have about IDs. And then the second thing only is turning this into a data frame. Okay? And then the final thing is, you remember that we have all those columns, bunch of them. Well, I want to turn them into actual rows and then name the column for them. So for that purpose, I need to transpose these, which in R is basically just T. All right? Okay, so once we actually do this, and once I actually run this, we can then inspect also this newly created data frame. And what we should see now is that we have, we should see actually two columns here, right? So actually we have one column, and this one is the distance, all right? What actually happened, why I expected two columns, is I expected that these row names are actually going to be a separate column. This is not the case, so we will need to make sure that we turn these row names into a separate column. So we're going to go ahead and create an object called shortest path, shortest route distance df. And then within this one, what we're going to do is we're going to get rid of row names, and before we get rid of them, we're going to turn them into a column. That means we need to do column-wise binding here, and we're going to create a column name for those that are going to be created from row names. It's going to be called edge ID. And again, this one is going to be the row names of this route distances df. Okay, and then one last thing here, we are actually putting together the old data frame with the new, which is going to have this edge ID. All right, so then if I actually run this, what you will see when I, for example, explore this newly created data frame, you should be able now to see that we have two columns instead of one, and here it is. So we have edge ID, which took the row names values, and then we have this one, which is distance, which has an awkward column name, which corresponds to the ID of the from location. And in our case, there's only one from location, so that's why I have this. So we have this data frame, but we're not really happy with it. So we want to change a bit of things. First of all, let's make sure this is a data frame. So let's turn it into a data frame. Second thing, let's change that awkward name. So let's use dplyr rename. The way this argument works is you first provide the new name that you want to use. So I would like to name it distance. And then you provide the second name here, or the existing name. And you remember it's that number. Well, in R, if a column is a number, you need to wrap it into this quotation marks. So this is what we're going to do. And then if I run this once more, what you will see is that we actually successfully renamed the distance column. So now we have edge ID and we have distance. Okay, that's cool. That's cool enough. But one thing that we also need to make sure is that this distance are actually, it would be nice that if it's numeric, all right? We don't need to, but we can also do that. Why are we doing that? We're doing that because I would like then to arrange these numbers. Currently, distance is a character string, and that's not good for us. So in order to basically turn this distance into a number, we can simply use mutate from dplyr, and then we simply say here the distance equals to as numeric and then also distance. And then we can of course arrange. So why am I doing here arrange? Because I would like to have the shortest route at the top. So I'm gonna sort this in ascending order. So here is how I'm gonna do that. In dplyr, there is another function which is called arrange, and we can arrange distance just like this. Okay. So this is basically now, if we actually run this whole thing, we should be able to see once again reshaped, of course, data frame, but this time you should see at the top which is the minimum. So the minimum distance is 2.8 kilometers, and here we also have the edge ID, which we will then use later to fetch exactly those lines that we need for our visualization. So that's the first step here. Now the thing is, there might be some duplicates here, all right? So there might be some duplicate rows, and we want to make sure that we take only distinct rows. So we can build this into a pipe here, and dplyr has a really cool function which helps us deal with duplicates, and it's called distinct. Okay, so here we need to pass the names of our columns. So that's edge ID, and that is also distance. And then we want to keep everything else if there is anything else. So in our case, we have only like 2 columns, so that's not necessary. But imagine that if you have more, then you would be using this. So this is just for demonstrative purposes. And then once you do this, what we can also do is only keep the shortest distance, all right? You can, of course, play with this. You can keep more, but I want to have only the shortest. So that's row number 1. And if I want to keep only row number 1, I can use slicehead from dplyr, which actually cuts a certain number of the first rows. And here I say I want to cut the very first row number 1. Maybe if you would like to have, let's say, the first 3 shorter routes, you can then put number 3. Okay, so the last step is finally to run this whole thing and then show you what actually we got. So if I run this, you will be able to see finally only one row where we have this edge ID and we have also this distance. Okay, and now we can use this information to find the shortest path among all the paths. And I'm gonna call that object shortest line. So the shortest line will start off from this df graph edges, so basically all the paths. And then it's gonna build a pipe here, and then it's gonna filter. So we will filter based on, we need to detect actually here, because you remember that string is quite long, so we need to detect. And we can use string R from dplyr, or sorry, from tidyverse for that. It has a nice option called str detect. So here what we want to do is, in the ID column of our df graph edges, we want to recognize, what do we want to recognize? We want to recognize the edge ID from our object, which is called shortest route distance df. All right, so once we actually run this, and once we actually inspect the first few rows of this newly created object shortest line, we should be able to see the following thing. So we should be able to see everywhere, so all the possible rows where the pattern was recognized. And how do we know it was recognized? Well, it's actually here, right? Now, one thing that you will notice here is this actually has a bit different numbers. So it has our base number, which then increases, which means that some things were added here. But we will deal with that later. For now, what is the most important thing? That we grabbed those lines that comprise a shortest path. The next thing is to extract these from our main street network, which actually has this SF line object. So in order to link that distance, the shortest distance number, to the actual pathway, what we need to do is we need to get those paths lists, we need to turn it into a data frame, and then we need to match the ID from the distances with the pathways and get the appropriate pathway. So that's why I said that it's kind of a bit complicated with dodgr, but we'll get to it. So the first thing is to create an object, which is going to be called df graph edges. And then we're going to actually put here this paths list that we have. And the first thing, we're going to unlist it. And then the second and the third step will basically be what we did with distances. And that is, first of all, turn it into a matrix. And then second, turn it into a data frame. Okay, so we can actually just run this. And then I want to show you how this object looks like. So now you can see that we have two columns, ID and V1. The V1 is the actual edge ID or the destination ID, which we need. So I will go ahead and basically make this one more appropriate, this name. So I'm going to go ahead and change the names for graph edges, but only for the second one. And I'm going to name it edge ID. In this final step, we will turn our street network, denoted by object G, into an SF object, and then we will use information from this shortest line that we just created to fetch those lines, the shortest pathway lines that we need. So I will create an object, which is going to be called shortest path SF. And before actually I jump into that, I first of all need to turn the G object into an SF object. So creating GSF object from, again, dodgr, and then another function here, which is also very useful. It's called dodgr to SF. So here I will just pass G, sorry. Now that we have this, we can go ahead and create this shortest path SF. So this one will be based on this GSF, and we will be filtering it. Okay, so I'm gonna go ahead, use dplyr filter. And then here, what do I want to do is, I want to get information from this 2ID, because this is what we essentially get from the shortest line. We got 2ID. So 2ID is going to be the main column from this GSF. And then because we have a list of different 2IDs, we need to use in argument in R, which is used for filtering lists. And then we only need those that are unique. So we only need unique shortest line and then edge ID. Okay. And then the very last step is to actually get rid of any streets that might be there, but that do not actually belong to only the shortest paths. So the way to do that is finally to intersect this object that we created with the original paths SF. Okay. So we can then actually run this, and then you won't be able to see right away the results, but the best way would be actually to visualize, to create this final plot. And in this final plot, what we can do is we can basically just go back to our code and get that work on this last ggplot2 code that we had, where we actually had several things. So we had Belgrade fuel, that's fine. We had our starting location. We also had different paths, which is also fine. So we can again have that. And then what we also want to have here now is exactly the shortest path. So for that purpose, I'm actually gonna first of all decrease here the size of this one. Let's make it 0.15, and also alpha could be a bit lower. Let's say 0.5. Now to this whole thing, what we're going to add is this newly created object, which is going to then mark, of course, the shortest path among the shortest paths, right? So I'm going to actually give it here a red color so that we can clearly see it. It's not going to have any alpha values. I want it to be dominant there. And I would like to make it a bit thicker here. So I'm going to just put 0.8 here. And then let's just check if actually we have everything here. So yeah, we have the street layer. We have the fuel stations, we have the from points, we have all those paths, of course, that are the shortest, and then we have the shortest among them. So then once actually you run this, what you will see is that clearly now we have that shortest path, which is 2 point something kilometers. We also have other paths. So if you want to consider, of course, where you want to go, from this specific location and get the fuel for your car, you can actually consult this map, which tells you in a straightforward way what is the shortest path among all these different paths. And this is how you compute and visualize the shortest routes to your points of interest. In today's tutorial, we did that on example Belgrade, but you can take this tutorial literally to any city around the globe, and I'm really looking forward to your own use cases. If, however, you would like to replicate today's analysis, I prepared the link to the GitHub repo in the description box below, so do check it out. Feel free to clone it, reuse it, modify it as you see fit. If you have any questions, comments, or feedback, feel free to reach out to me here on YouTube, but also on Instagram and X. If you're new to R and you seek to expand your data visualization and geospatial knowledge of R, I prepared a few cool tutorials for you, so do check them out. See you next time.